of converging and diverging series, so let's remind ourselves of what a converging and diverging series is about. And so this is about geometric sequence and geometric series, and the sum of terms in a geometric series is given as the first term times 1 minus r raised to n upon 1 minus r. I could also write it as r raised to n minus 1 upon r minus 1, doesn't matter. Now look at the common ratio. If r is greater than 1, what happens to r raised to n? As n increases, r raised to n also goes on increasing, it becomes bigger and bigger. So the series, the sum value also goes on increasing, and therefore it is called a diverging series. So if I had taken a very large number of terms, then it would have reached a significantly large value, which is the idea of diverging. Whereas if r is less than 1, which means a fraction, then r raised to 1 is going on decreasing, because a fraction multiplied with itself goes on becoming smaller. So at one point r raised to 1 will become negligible, and this is the condition for a converging series. And what does it converge to? Well, if we write down again the value, r raised to n is becoming negligibly small. So if I ignore this, I will be left with u1 upon 1 minus r, and this is what is called the sum to infinity. That means when, and I know infinity is not a number, but if n is sufficiently large, then r raised to n will be negligible, and the series will converge to the value of u1 upon 1 minus r. And this is a concept that is useful in many cases, and we will look at some examples. So let's start with an example of first finite numbers and then to infinite. So the first application is in financial mathematics of a recurring deposit. So at the beginning of every year, I deposit $1,000 in a bank account which earns me 7% annual interest, and compounding also occurs only annually. So let me see how the money grows if I have the same amount, if I'm repeating that for 50 years. So what happens at the beginning of the year and what happens at the end of the year? So in the beginning of the year, I had $1,000 in the first year, and at the end of the year I would earn 7% interest, and my money would grow to 1000 times 1.07. In the beginning of the second year, so this is the first year, beginning of the second year, I have earned interest, and then I deposit another new $1,000, because at the beginning of every year I'm doing that. So at the end of the second year, I would earn 7% interest for 2 years on the first $1,000, and 7% interest for 1 year on the second $1,000. At the beginning of the third year, I would have earned interest for 2 years, the first amount, 1 year, and I would deposit one more 1,000. So at the end of the third year, I would have earned 3 years interest on the first $1,000, 2 years interest on the second $1,000, and 1 year interest on the third $1,000, and this goes on. So if I look at the end of 50 years, what I would essentially have is the first $1,000 would have earned interest for 50 years, the second $1,000 would have earned interest for 49 years, till the last $1,000 would have earned interest for 1 year. Correct? If I take 1000 times 1.07 common and notice my terms inside the bracket, it is not hard for me to know that this is a geometric sequence with 1.07 as my common ratio. Is the ratio greater than 1? Yes. So is it a diverging one? Yes. But only it is going to infinite value only if n is very, very large, right? Here n is a finite number, which is 50, so shouldn't be a problem. So 1000 into 1.07 times the sum of terms formula. First term into common ratio raised to n minus 1 upon, so this is the total amount that I will have in my account, correct? This is one of the applications that we see. A second application is in number theory. So a recurring number, right? And I'm trying to see how this number can be written as a rational number, correct? So all recurring numbers can also be written in the form of a fraction. So I'm writing, and let me rewrite this number and expand it to write it this way. Right, the same number. So the first number is 23 by 100. The second number is 23 by, and instead of 100, let me write it as 10 raised to 2. Second is 10 raised to 4 plus 23 upon 10 raised to 6, and so on. Can I take 23 upon 100 common? Then what will be left in the bracket is 1 plus 1 upon 10 square plus 1 upon 10 raised to 4, and so on. Not difficult to see that this is a geometric sequence or geometric progression whose common ratio is 1 by 100. Is the common ratio less than 1? Yes. Are there infinite terms in this? Yes, because it's a recurring number, so the decimals will go on. So what I'm seeing inside is a infinite geometric sequence with r less than 1. So it must converge to u1 upon 1 minus r, which means first term upon 1 minus the common ratio, which is 23 by 100 into 1 upon 99 by 100, which means 23 by 99 is the number that I can write it to. So the recurring number got written as 23 by 99, and again the concept here I used is an infinite geometric sequence, right? One more interesting thing is fractals. So fractals are often repeated patterns. So let's start with a simple fractal example. So I have a equilateral triangle, and I'm saying that I start with a side of 9, okay, and I'll write down the area and perimeter for each of the diagrams that I'm drawing, and see how I will use the same concept of converging and diverging series in this example of geometry. So write down what is the area. Perimeter and area is what I'll write down. So I have 3 sides, each of length 9. So that's my perimeter. And area for an equilateral triangle is root 3 by 4 into side square. So that's my area, correct? This is for the first diagram. Now what I do is I connect the midpoints of the sides of this equilateral triangle, and I remove this triangle at the center. So what I'm left with now is a diagram which has 3 equilateral triangles. However, the sides of this equilateral triangle have now become 9 by 2 each, correct? So how many, now what is the perimeter and area? Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9 sides are there, each of length 9 by 2. I may also want to write it as, I'll leave it as 9 by 2 times 9, or 3 by 2 times 27. And I'm purposely doing this because I want to see if there is some relation with the first term. Okay, so first term is 27, right? The first perimeter. So therefore, now what about the area? There are 3 equilateral triangles, each with sides 9 by 2. So 3 equilateral triangles of side 9 by 2. Again, can I write it in terms of the first term? So I want to write it in the terms of first term, then 3 by 4 times whatever was the first area, right? So if this is A1, then I'm getting this as 3 by 4 A1. Okay. The next time I go back and I again do the same thing. So I do the same exercise. I connect the midpoints of each of these triangles and I remove this portion. So fractals essentially are like repeating the same pattern again and again. Okay. Now what is my side? Each side, how many triangles do I have now? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I had one triangle, then I had 3 triangles, and then now I have 9 triangles. So the number of triangles are also increasing in a sequence somehow. So what is my perimeter going to become? There are 9 triangles, each of side 9 by 4. But I wanted to preserve the first, the 27, right? So I'll take 27 outside. So what will be left is 9 by 4, 3 by 4 times 27. Let me just check. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles, each with length, so there are, each has 3 sides, so 9 by 4 times 27 is the perimeter. And how many triangles do I have now? 9 triangles, each with area of root 3 by 4 into side square. Again, if I want to keep A1 as it is, then what is the term that comes out is A1 was root 3 by 4 into 9 square. If I keep that as it is, I get 9 by 16 times A1. And if you repeat, it's not hard to see that the perimeter was 27, then it became 3 by 2 times 27, then it became 9 by 4 times 27. This is how the perimeter is growing. So the common ratio is 3 by 2, which is 1.5, which means ratio is greater than 1. And the area, it was root 3 by 4 into 9 square, then it became 3 by 4 times the first area, then 9 by 16 times the first area, and so on. So the common ratio here became 3 by 4, which is less than 1. So if I had continued forever, then my perimeter would be a diverging series because R is greater than 1. And my area would have been a converging series because R is less than 1. And it's strange that perimeter is growing infinitely, but area is remaining same. And that's one of the interesting points of fractals, is that the perimeter goes on increasing, and very common examples are the coastline. Also you would see that even tumors areas are being calculated using this concept, that the perimeter goes on increasing as the cells grow, but the area remains finite, and therefore they are using the idea of fractals for finding out the area. So this is another example, and the final example that we would look at again is in financial mathematics, and this time instead of accumulating, I'm withdrawing money, right? So let's take the same example that I had $1,000 and I was earning 7% interest, and I kept the money for 20 years. If while depositing I'm also trying to withdraw some money, okay, X amount, not $1,000 really, some smaller amount, then how long will I be able to sustain that I still have money left and I can withdraw? correct? So if I keep this money for 20 years, how much interest will I earn? 1.07 raised to 20. Correct? That's the compound interest formula. However, I am withdrawing. So every month I am losing some money. So the first month I would lose interest. If I am withdrawing X amount every month, the first month I am withdrawing, I'm losing 7% interest on this X. The second year I would lose interest for 2 years on the first X that I withdrew, and I would lose interest for 1 year on the second X amount that I will withdraw. In the third year I would lose interest for 3 years on the first X amount that I withdrew, for 2 years on the second amount that I withdrew, and 1 year for the third amount I withdrew, and so on. Till when will I do it? Obviously for 20 years I'm withdrawing. So by the end of 20th year, the first X that I withdrew would have lost money for, lost interest for 20 years, then for 19 years, and the last one for 1 year. This amount must be equal to how much I earned by keeping this $1,000 for 20 years. Correct? So whatever I earn, this must be equal to the remaining thing. So on the right hand side you are seeing that it's a geometric sequence, of course, it's with finite number, and that's equal to the total amount that I will have in my account. So how much can I withdraw is another application that can be done. This can also be thought in terms of repayment of loan, like the left hand side could be the loan amount, and then you are repaying some amount every year, so finally it will be repaid after some X number of years. So you could either think about years if you know the payment made every year, or you could think of payment every year if you know the number of years by which you want to repay the loan. EMI, like installments. So these are some common examples that are available for converging and diverging series.